Alright, so before the test gets going, and now that I've got most of these submitted, I want to go over the graded and reviewed questions. Just three, so we'll start off with the first one here. This is the one where you were given three forces acting on an object, and you were asked after a certain amount of time, where is it? So what that means is you're going to have to figure out, well, a delta x value and a delta y value. So it's looking for a position. It's looking for this final answer of some kind of a coordinate. Now, to simplify things, we're going to say this object is starting at the origin. It's starting at rest, so vi is 0. And we know the t of 3, so we need to figure out eventually what vf is, and then work through some of our kinematic equations from earlier this year to figure out a delta x and a delta y based on the acceleration and the vf and the vi. Okay? So to work through that all, you need to first break everything down into its components. You need to find f1x, f2x, f3x, and then f1, 2, and 3 y's. Now for x, you're going to be using, for f1, I'm going to say that's the one in the top right quadrant, you're going to be using the cosine function for x, the sine function for y. F2, that one, it's again cosine x, sine y, because those angles are measured off of the x-axis. But for the other one, the angle of 18 degrees, that's off the negative y-axis. So if that angle is here, so that's this diagram here, if that angle is located at this point, then x is now opposite and y is adjacent, so we had to flip the functions there. So we use sine for x and cosine for y. So if you work through all of those, you're going to get those 6 values for your individual component forces. Now we need to know what our total net force is here with these, and we're going to use the F equals ma equation here to figure out our eventual acceleration. But to figure out that acceleration, we're going to say we need to find out this F first, which, kind of working through equations here, this net force, this F, is the same as this one, the sigma F. And this equation here is our Pythagorean theorem given our two net force components. So once we know what F net x is and F net y is, we can figure out what F net total is. And then we're going to come down here and actually find out what x and y are to eventually plug it into that equation. So start off with our F net x. We're going to do 1x minus 2x and 3x because 1x is to the right, 2x is left, and 3x is again to the right. So we have the 17.4 minus the 21.8 and the 6.8, and then adding the 6.82, you come with a total net force in the x direction of 1.8. Go through and do your y components. 1 and 2 are in the positive y direction, 3 is in the negative. That works through to a total F net in the y direction of 4.4 newtons. So now that we have these two parts, we're going to kind of come back up in here and solve for the F net total. So that's this equation. The F net total squared equals Fx squared plus Fy squared, and that works out to a total F net of 4.8 newtons. We can then take our total F net, plug that into the F equals ma equation that we had up top. The mass of the object was given as 4, so we're using this equation, F equals ma, plugging in 4.8, mass of 4, we get an acceleration of 1.2 meters per second squared. So if the object is at the origin, it's going to accelerate at 1.2 meters per second squared. Now, we have that acceleration, we should also figure out, say, our VF. So I believe that was one of the questions there. Well, we know VF initially was 0. We had our A we just solved for is 1.2, our time of 3 seconds. We can work through and get a VF of 3.6 meters per second. So now we know what velocity this thing is traveling in. And with the velocity, we need to know what direction as well. So we're going to go ahead and do the inverse tangent function of our F net y over F net x to tell us which way. And we get an angle of 67.8 degrees. That should not be newtons there, it should be degrees. Now, which direction is this in? Well, we said our F net x was a positive 4.8. F net x is a positive 1.8, and our F net y is a positive 4.4, so we're in that top right quadrant. So we drew this little diagram here. We have 67.8 degrees is the angle it's acting at. We're going to look for this point, delta x, delta y. Where does it end up? Well, we need to figure out the distance that this goes. We know the velocity is in this direction. So the displacement, or the distance it travels in, is also this direction. So if we do the distance equation, which would usually be written as delta x equals so on, I'm going to put d here instead, since we're going to have a point delta x and a point delta y, just to alleviate confusion. So we have d equals vit plus 1/2 at squared. Thing starts off at rest, so vit portion is 0. Plug in our acceleration of 1.2, our time of 3 seconds, we get that it travels 5.4 meters. So this d value here is 5.4 meters in total that it travels from the origin. Now if we know that's how far it goes in total, to get that point, we need to be able to reference that as a coordinate. So we need the delta x side of this distance and the delta y side, the components of the distance, or the displacement. So delta x equals d cosine theta, 5.4 cosine of the angle we found earlier, and then 5.4 sine of the angle earlier, and we get two different points. We get delta x is 2.04 meters, and delta y is 5 meters. So coming back to our thing up here, our final answer then is what was already stated earlier. The location of the object is going to be 2.04, 5 in terms of how far it goes or where it ends up precisely. So that's it for number 1. Finding VF, finding A, and then eventually locations. But to get to those things, we have to solve for multiple other things in the process. Now I want to go ahead and go to the next one. This is number 2. We are given an object that is on a slope, and the angle of the slope was 28 degrees, so this was your theta value. And I'm trying to think what else was given in the problem. It gave you the mass of the object, so you're given m equals 10 kilograms, and you were also given 2 different coefficients of friction. So we were given that the mu static is 0.8 and mu kinetic was 0.3. So that's all we knew about the situation. We first wanted to figure out how much force was necessary to get the thing moving. And then after that, if we continue to apply that same amount of force, what would be the acceleration of the object? And then eventually, once you know that acceleration, how far do you have to push the thing to get to a certain velocity? The velocity that one was 2.6 meters per second. So we're taking our forces and frictions at an angle and then mixing in some of our old kinematic equations on top of that. So to start off with, we need to create the free body diagram, which is shown over here. You have the force of gravity acting straight down, you have the applied force acting up, normal acting perpendicular to the surface, so that puts it up and to the left, and the force of friction down. That's opposite to what we normally have, because friction we usually consider up the slope. But in this case, since we are trying to move this thing up the slope, friction is working against us. Friction is always working against the direction of motion. And since we're trying to go up this ramp, the force of friction has to go down. So now that we have our diagram started, we can go ahead and make some statements. We're looking for FA, that's our question mark. How we're going to find out FA is by looking at the net force in the x direction being 0. Now, net force in the x direction of 0 means it's stationary or it is moving at a constant velocity. In this case, we're trying to get it moving. So we're looking for a F net of 0, and if we can find out what FA would be to get this, then whatever we need to do to get this thing moving is going to be an FA of just slightly more than whatever we solve for. So if we get it takes 40 newtons for FA in order to this to be 0, then to get the thing moving we need to apply FA greater than 40. So we're going to go with our F net x equation. And in our x direction, we have FA, which we're going to consider up the ramp as positive, minus our force of friction, minus our force of gravity in the x direction. So we're going to say 0 equals FA minus FF minus FGX. Well, we need these values of FF, and we need a value for FGX. Well, FGX, we know that FGX is the equation mg sine theta. Given the mass of 10, the angle 28, we can solve for an FGX of 46.1. And then for the force of friction, we're going to do mu times force normal. And we don't have force. We don't have normal force yet, but we do know that the normal force is equivalent to FGY. So we can rewrite our mu Fn as mu FGY. So we get mu mg cosine theta, and running through with 0.8 as our value for mu. Since the thing is currently stationary, we deal with mu s, the mu static, and we get a force of friction of 69.2 newtons. So now we can come over here and plug in these values we have for FF and FGX. So carrying on to 0, we get 0 equals F8 minus 69.2 minus 46.1. And then we get an applied force, an FA of 115.3 would yield a net force of 0. So to move the object, we have to have a net force greater than 0, so we know FA has to be greater than 115.3. So that's going to be the first answer to this question. What is the minimum force necessary to apply to get the object moving up the slope? Now for the next part, once this thing is moving, we're going to continue to apply this 115.3. Once it's moving, what is its acceleration and how long does it take it to get to 2.6 meters per second? And how long being in terms of distance, how far do you have to push it? So we're going to go with our F net x equation again. This time it's not a 0 because the thing is accelerating. We need to figure out what it is. So our F net x is going to be, again, FA minus FF and FGX, same forces acting, same directions that they're acting in. This time we know what FA is, our 115.3. We can solve for the force of friction again. We're working at this equation. We can resolve for this force of friction using our different mu value. And FGX is going to be the same, right? Because it's still the same gravity, still the same mass, still the same slope of the surface. That value doesn't change. So we come down here, we plugged in our 115.3. We plugged in the mu kinetic of 0.3 because now this thing is sliding. We don't use static mu anymore. And our 46.1. We get a total net force in the x direction of 43.2 newtons. So this is being our net force, we can then figure out our acceleration. So F net x, going to plug into the F equals ma. 43.2 equals 10a. We get an acceleration down here of 4.32 meters per second squared. So that's how quickly this thing accelerates up the surface of the ramp. We want to get this VF of 2.6 meters per second. The thing started off at rest, because we had to get the thing moving. We're given the a value that we just solved for, we look for this delta x. So the equation we're going to jump to is one of our kinematics, the VF squared equals VI squared plus 2a delta x. Plug in our a, plug in the VF we're looking for, solve for delta x, and we get a total distance up the ramp of 0.78 meters before it's at a 2.6 meter per second velocity. So this one, again, braking forces and components, creating that free body diagram, solving for F net x's, F net y's, working through to get your totals, and then accelerations and wherever else from there. Now for the last one, 3, that one is either very difficult or very simple, depending on if you picked up on something. With that one, you are given the slope of the, no, you're not given the slope of the surface, you're given the mu value. Okay, so let's check that. The mu value was 0.8 for mu kinetic. Or mu static of 1.5. You're asked what is the maximum angle that this person can walk up, basically in terms of a slope. So what you can do is recognize something, and that is if you're trying to walk up a slope or try to move something on any kind of an incline, then you're going to be dealing with static friction, because static friction is going to be the highest amount of friction you can get. As soon as you start dealing with kinetic friction, then that value drops and there's less there to propel you up the slope, so the thing tends to just slide down. Like you'll notice that as soon as you start walking up the slope, you're good until you start to slip a little bit, and then you're just going to lose traction. You're just going to run down the slope unless you can manage to regain static. So we're not going to really be concerned with mu kinetic here, because mu kinetic is going to give us a lower value than what mu static is going to give us in terms of the maximum angle at which you can walk up. Now, that angle is going to be related to a term called the angle of repose, which, if you stopped in during some of the office hours, you would have caught this part. You might even have this on your equation card. That angle of repose is the maximum angle that you can have between two surfaces or something can be sitting at before it breaks loose and gives way to kinetic friction. Every combination of surfaces has a different angle of repose. That's why when you drive by one of those facilities that sells mulch or gravel or something, you'll notice that all of the piles end up being at different angles. That's because each of the different materials have a different mu value, right? Which corresponds to a different angle in which it can be piled before it breaks loose and starts to give way and slide off. So we can jump to an equation for this, and that is theta r, angle of repose, equals inverse tangent of mu s. And you can go straight to the answer of the problem by going inverse tangent of 1.5 to get theta r. And that's it. Maximum angle you can walk up is 56.3 degrees. As soon as the slope gets higher than that, the shoe is no longer going to be able to maintain static friction, and it's going to break loose and start to slide. You can also get this by like a derivation. That would have been similar in process to the assignment prior to this one, which was dealing with the question that was the most massive car in the world was sitting on a slope question. In that one, you didn't know the mass of the object, so you end up doing a lot of canceling of things out. In that case, you knew that the force of friction acting up the slope is equivalent to the force of gravity in the x direction pulling you down the slope. You know the force of friction is equivalent to mu times force normal. This is equivalent to Fgx. And we know that force normal is the same as our Fgy. So mu Fgy equals Fgx. So moving things around, we get mu equals the x component of gravity divided by the y component of gravity. And then plugging those in further, Fgx is mg sine theta, Fgy is mg cosine theta, the mg's cancel out, and sine over cosine is tangent. So you get that equation, and that equation is for static friction and for the angle of repose. So then you just have to rearrange that to get the theta r equals inverse tangent of mu s. So that's it for the review questions. Go back, look at your answers if they're, and see if they match up with these. If you have any questions, stop by during office hours. The test is going to be coming up here, like I said, on the 17th. So we're going to have a review day before that, and also just an open kind of a study day. So I'll just set aside a couple hours specifically for class. You'll be required to check in at some point, either by logging into the meeting or posting some kind of a comment with at least one question that you have about the material from this unit. Okay, so go ahead and work on the other thing that's not posted, and have a good rest of your day.